Hey everyone, and welcome to The Explainer. Today, we're taking a magnifying glass to a massive central mystery in the world of artificial intelligence. We hear a lot about vision language models, right? These incredibly powerful AI systems that can supposedly look at a video or an image and just instantly understand what's going on. But the real mystery we're unpacking today is this. Do these models actually understand the physical 3D spaces around them? Or are they just incredibly good at faking it? Now, you might be wondering why this matters. Well, this isn't just some academic question. It's absolutely critical. Because as we start deploying AI into the real world, putting it in home robots, self-driving cars, smart assistants, we desperately need to know if it can truly see its surroundings. I mean, if an AI is going to navigate your living room or help out in a hospital, it needs genuine spatial intelligence, not just a really good guessing game. Okay, let's dive into this. Here's our roadmap for today. First, the spatial intelligence test. Second, flaws in the grading. Third, introducing the ReVSI benchmark. Fourth, who really performs best. And finally, exposing AI hallucinations. Let's get right to it. Starting off with Section 1, the spatial intelligence test, and how we actually gauge these vision language models. To start us off, we need to establish exactly how developers currently measure a model's ability to perceive 3D environments. Basically, how do we give an AI an eye exam? Think about a chaotic, cluttered real-world kitchen. When an AI looks at a scene like this, it isn't in some neat, perfectly organized lab. It has to parse an overwhelming amount of visual data. It needs to answer complex questions about relative distance, like is the blender closer to the sink or the oven? It has to estimate object size, and even just accurately count how many cabinets or appliances there actually are. For a while now, the standard exam that these AI models have been taking to prove their spatial smarts is called VSI-Bench. It stands for Visual Spatial Intelligence Benchmark. It's essentially this massive data set of questions and answers based on video streams of indoor spaces. And the thing is, the entire industry has relied heavily on VSI-Bench. We all just operated under the fundamental assumption that it was an accurate, objective measure of an AI's spatial intelligence. Which brings us to Section 2, flaws in the grading. The broken answer key. So what happens when the standard test the whole industry relies on is actually deeply, fundamentally flawed? Well, researchers recently realized AI models were being heavily penalized for giving wrong answers when the grading key itself was actually incorrect. It turns out VSI-Bench suffers from two massive issues. The first is annotation drift. This just means the test uses old, repurposed 3D mapping data that is often just plain wrong. The second issue is observability mismatch. This is literally when the test asks the AI a question about an object that has been completely cut out of the video clip the AI was actually given. Imagine taking a test on a chapter of a book that was ripped out before you even got it. Now, what's really interesting here is looking at these fragmented, glitchy digital meshes. This is the exact kind of early 3D point cloud data that VSI-Bench was using for its ground truth answer key. Because the 3D reconstructions are so noisy and incomplete, the test's answer key ends up completely corrupted. It mislabels objects, it gets room sizes totally wrong, and it essentially forces the AI to try and learn from garbage data. And it actually gets worse when you look at the statistical biases baked into that old test. Take object counting, for example. The VSI-Bench test was built in such a way that the answer to how many of this object are in the room was the number 2 a staggering 53% of the time. That's absurd. It means an AI could literally just close its digital eyes, blindly guess the number 2 for every single counting question, and automatically pass the test with flying colors without doing any actual spatial reasoning at all. Moving right along to Section 3, introducing the ReVSI benchmark, fixing the test. Clearly, we desperately needed a solution here, a repaired, rigorous way to measure spatial intelligence. Let's see how this builds and compare the two approaches. The old, broken, highly noisy 3D mesh of a bathroom that VSI-Bench relied on is full of holes. But the new solution, ReVSI, uses meticulously re-annotated, perfectly clean 2D room boundaries, created and verified by actual humans. They threw out the glitchy auto-generated maps and literally drew the answer key by hand.
And the quality upgrade is massive. They didn't just fix the errors, they scaled the whole thing up. ReVSI expands the testing ground to 381 detailed scenes. But even more impressively, it jumps from just 65 basic object labels to 504 precise open vocabulary labels. So the AI isn't just looking for generic chairs anymore. It's being tested on specific human-verified items like a black office chair or a Coca-Cola box. It's a much, much harder test.
But honestly, the most brilliant fix is ReVSI's frame-aware protocol. Remember that observability mismatch issue we talked about, where things were cut out of the video? ReVSI fixes it by ensuring absolute fairness. It tests models based strictly on their specific frame budget, whether the AI is processing 16, 32, or 64 frames of a video. Crucially, the protocol guarantees that the AI is only ever tested on visual evidence that actually exists within those specific frames. If the target object is invisible in the 16 frames the AI was handed, the question is thrown out. No more trick questions. All right, section 4. Who really performs best? The surprising results. So what actually happens when you finally give these AI models a fair, perfectly graded test? When we map out performance across tasks like object counting, relative distance, and room size, we see something wild. Under the flawed VSI-Bench, open source models seem to be winning the race. But on the repaired ReVSI test, proprietary models like Gemini 1.5 Pro actually vastly outperform the open source ones. Fixing the answer key completely reversed the false narrative that the entire industry had bought into. And get this, the researchers also discovered something fascinating about how we actually train AI. For a long time, developers have been fine-tuning their models by feeding them massive amounts of 3D spatial data. But on ReVSI, these heavily fine-tuned models showed incredibly small gains. And shockingly, some actually performed worse than their basic, untrained counterparts. It proves that scaling up bad, noisy training data doesn't help at all. If you train an AI on a broken answer key, its genuine 3D reasoning skills will actually get worse.
Finally, section 5. Exposing AI hallucinations through the dummy video stress test.
Think about this. If the open source models were doing so well on the old test, but terrible on the new one, how on earth were they getting the right answers before? To find out, researchers created a brilliant trap. Here's how they caught the AI cheating. Step 1. They took an ordinary video scene. Step 2. They intentionally deleted every single frame that contained the target object, scrubbed it completely from existence. Step 3. They asked the AI a spatial question about that completely missing object. It was a stress test to see exactly what the AI would do when the visual evidence was 100% gone.
And here is the gotcha moment. When presented with these completely scrubbed dummy videos, many open source models still confidently guessed the correct object attributes. They passed the test without actually seeing the video. How is that even possible? Well, because they weren't doing spatial reasoning at all. They were relying on memorized statistical priors. They basically learned that, hey, in a bedroom, beds are usually this big and there are usually 2 pillows, and they just guessed based on those vibes, entirely ignoring the actual visual input they were given.
To really cement this, let's look at a direct quote from the researchers themselves. They wrote, "Several models still achieve surprisingly high scores, revealing predictions driven by non-visual priors rather than visual evidence." Guys, this is the textbook definition of AI hallucination in a spatial context. It proves beyond a shadow of a doubt that many models that seem incredibly smart are actually just highly sophisticated guessing machines relying on their training data biases rather than utilizing true visual intelligence. Which leaves us with this final, incredibly provocative question to think about. As we integrate these tools into our daily lives, from home robotics to autonomous vehicles, is your AI truly seeing the physical world around it? Or is it just guessing based on its training? The ReVSI benchmark has finally given us the lens we need to tell the difference. Thanks for joining me on this explainer, and keep your eyes open.